Welcome back, everybody. This is our 5th video on numerical integration. In this video, we're going to look at what are called error bounds. So error bounds are going to be a way of describing how, when we use one of our numerical integration techniques, like the midpoint rule or the Simpsons rule, just how badly they could be off, at least if we know some nice things about the function. Now, we're only in this video going to apply it to Simpson's rule, but if you go into your textbook, you'll be able to find various formulas for midpoint rule and the trapezoidal rule. All right, but you should get the idea from this video. All right, let's begin. So we're going to make an assumption that our function, you can differentiate it a lot. All right. In practice, you don't need it to be differentiable forever. But we're just going to assume that we're always dealing with very, very smooth functions. What do I really need? I need fourth derivatives. So recall this notation here for if I want to take a higher derivative, I put parentheses around the number. This does not mean f to the fourth power. It means the fourth derivative of x. So I'm going to consider this function, f to the fourth, on the interval where I'm integrating. So in the back of my mind, I'm thinking, oh, I'm trying to integrate my function f from a to b. And so I'm going to consider the fourth derivative of f. So random, right? The fourth derivative of f on the interval ab. Okay, and you remember, if I use these square brackets, it means it's a closed interval. It means I get to include a and b in that interval. Okay, I'll use parentheses if I don't want to include the endpoints. So I'm interested in this function. In particular, I'm looking at, I want to know what is the max of this function. What is the largest value that the fourth derivative of f takes when I'm on the interval ab? Now, how you find that, well, that's really a calculus 1 thing, right? You have some function. Doesn't matter that it's the fourth derivative of something. You have some function. I want to maximize it on a closed interval. That's the extreme value theorem, right? That's exactly what we want to use here. So I'm going to assume that you can do that. If not, you need to go back and learn that. Go to your instructor, watch a video online. Okay? But for now, we have to assume you know the extreme value theorem. Okay, so let's say I could find this maximum. Somehow, some way I find it. And I'm going to give it a name. Okay, I'm going to call this m. Okay, now I have to be a little careful here. I don't want to distinguish between this fourth derivative possibly having really large negative values that I don't count because I'm only looking for the max. So I am going to put absolute values here. So I only care what's the biggest. You know, negative 50 would trump 7, right? Because negative 50 is really big, even though it's negative. Okay, I just care about the absolute value. So my m will be the max of the absolute value of the fourth derivative. Okay, so the rule is going to be this. When it comes to error, I only care about how far away it is, not in which direction it is. So I'm going to use absolute values so that I don't have to worry about positive or negative error. The error in Simpson's rule is going to be bounded by, so less than or equal to, a fraction. Okay, what's going to go into this fraction? Well, in the numerator, I get this m, this max value. So somehow, the absolute value of the fourth derivative of the function on this interval is important. Who knew? Okay, it's actually going to be a bound on the error I get using Simpson's rule. Okay, modulo some other numbers. So what else do I need? I'm going to look at the length of the interval. So that's b minus a, the length of the interval. And I raise it, again, this seems like magic, I raise it to the 5th power. Whatever. Okay, now there's a denominator here. What's going to be on the denominator? So first, there's this strange constant, 180. And then, well, you see, when I say I'm using Simpson's rule, you remember, I have to chop up my interval into partitions. How many did I use? All we know is that it should be some even number of partitions. Okay, we're going to label that number by n. And so I'm going to here divide by n to the 4th power. Okay, so n is the number of partitions. Okay, So if I want to know how bad my Simpsons rule approximation is, right, or at least could be, I just compute this quantity. Now there's a little bit of work there, right? I got to somehow work out this fourth derivative. I got to find the max value of the absolute value. Oh my gosh, right? But somehow I compute this m, and then the rest of these numbers are pretty easy, right? The n, you just know how many you're using, right? Or the b minus a, well, you know the interval. Just compute that difference, okay? That's not too bad. And this will not tell me the exact error. Of course not. Why? If I knew the exact error, I would just add that into my original function and I would know the exact value. We wouldn't really need a rule for approximating anymore. We'd have the exactness. No, instead I'm just knowing this is as bad as it could be. Maybe this number is way bigger than my actual error. But what I can know for sure is that the error will be no bigger than this number. All right, let's see an example of how we use it. So typically, we're going to use it in a backward direction. That is, I want my error to be less than some amount. Okay, I need to know the area under this curve, and I need it to be within, say, 1/1,000,000th, right, of a whatever the unit is. I need to know what's my n. How much should I partition this so that I'm getting a close enough approximation? Right? And maybe when I work out what that n is, I go, oh, that's too big. It's too big because I can only afford 10,000 data points. I can't afford 1 billion data points. So in that case, you might say, well, fine, I'm going to need to either find another approximation technique, or I'm going to have to find out, do I really need my accuracy so tight? All right, so let's do an example. So in the example, I want to find my n such that when I compute the integral from 1 to 2 of 1 over x squared dx, computed using Simpson's rule, well, what I want my error to be, I want my error to be, say, less than, say, 1 over 10 to the 5th. So, has error less than 1 over 10 to the 5th, or 10 to the negative 5th, if you like. Okay, that's what we want to do. Okay, maybe we'll clean this up, and then we'll work this example. Okay, now that we've got the board cleaned up, we're going to try to solve this problem. So we know that the error is going to be bounded by this number m, which was the max of the absolute value of the fourth derivative of the function, which is 1 over x squared. The rest of this is not so bad. Okay, let's write it down. Say our b, well, that's 2. Our a is 1. So our b minus a is 1. So this 1 minus rather 2 minus 1 to the 5th is just 1 to the 5th. Hey, that's going to go away. The n, well, we don't know n because we're trying to find it. So I don't have to find the n. But there is still this m here. So I'm going to have to work out what this m is. So let's try this. So I'm going to need derivatives. My function is x to the negative 2. That's 1 over x squared. I need the fourth derivative. Okay, let's give it a try. So the first derivative is negative 2x to the negative 3. Second derivative is 6x to the negative 4. Third derivative is negative 24x to the negative 5. And finally, the fourth derivative is 120x to the negative 6. Whew. Okay. And I'm going to rewrite this because I understand this better as a fraction. I want to know on the interval 1 to 2, when is this biggest? And in this case, that's not that hard of a problem. We know that as you make x bigger, when it's a positive number, when you make x bigger, the denominator gets bigger. As the denominator gets bigger, the fraction gets smaller. If the fraction is getting smaller, you're definitely not getting more maximal. So if we want this to be as big as possible, we want the denominator to be as small as possible. And the smallest we can make it is when x is equal to 1. So the fourth derivative, and we can put absolute values here, but it doesn't matter because, well, for x between 1 and 2, everything is positive. But we'll put them for now. This has max 120 over 1 to the 6th on the interval 1 to 2. And of course, this is just equal to 120. And so that's our m. Okay, so I found my m. It's 120. So I have my m, I have my b minus a to the 5th. That was just 1. All I need to do is work out what my n is, but how do I figure out the n? I need this piece of information. I want the error to be less than 10 to the negative 5, which means I want this quantity to be less than 10 to the negative 5. Okay, fine. So we have our m. Let's see, we have our error first. We know that's bounded by our m, which is 120, times our b minus a to the 5th, that's just 1 to the 5th, over 180, times n to the 4th. And I want this to be less than, well, not even less than or n, 10 to the negative 5. In order to do this, I just need to solve this equation for n. Okay, this is not really that complicated. I'm going to multiply both sides by n to the 4th to get the n to the 4th over here. I will multiply both sides by 10 to the 5th. That'll put the 10 to the 5 on this side. So this is equivalent to saying, let's see, 120 times 10 to the 5th over 180 is less than n to the 4th. Well, I don't want n to the 4th, I want n. But, okay, I'll take a 4th root. So if I take a 4th root of everything, 4th root of 120 times 10 to the 5th over 180 is less than n. Okay, and this is where, I'm going to say I need a calculator. Fine, I go to my calculator, and it turns out that this 4th root of 120 times 10 to the 5th over 180 is about 16.07. Okay, so we end up needing that n needs to be greater than 16.07. Now, if we stop here, we're right. We do need to find this n, and n does need to be bigger than this. But we could actually be a little clearer here. All right? What's the minimal n? Well, first, n needs to be the number of partitions. That's a number. Okay? It's not going to be 16.1. So what's the next biggest number? Well, it'd be 17. But don't stop there. We're using Simpson's rule. And we had this little rule about Simpson's rule, which is that the number of partitions had to be an even number. So I can't use 17. 17's not even. I have to use the next highest number. I have to use 18. So the minimal n is 18. Okay, so that's not too bad though. If you want to get within 10 to the negative 5, integrating this function from 1 to 2, you only need 18 data points. Right? And in a world of big data where you might have thousands and thousands of data points, 18's not so bad. Now, this is going to take a lot of practice. You're going to have to do it in a lot of different contexts, trapezoidal rule, midpoint rule, but keep coming back. The method is going to be very much the same each time. Get your practice in. You can do this. I know it's difficult, but I believe in you.